Hello, my name is Nathaniel Weinman, and I am a PhD student at UC Berkeley. I will be talking to you today about Forkit, supporting stateful alternatives in computational notebooks. Computational notebooks, which seamlessly interleave code with results, have become a popular tool for data scientists due to the iterative nature of exploratory tasks. However, notebooks provide a single execution state for users to manage through the creation and manipulation of variables. Other work has explored supporting revisions in notebooks. Janice, from Rule et al., adds functionality to hide cells or view previous versions. Verdant, from Carey et al., allows data scientists to navigate through previous versions of a notebook. Gather, from Head et al., supports users in producing ordered code that reproduces certain results. These works all focus on the visual content of the notebook, while our work focuses on the execution state. When exploring alternatives, such as different data processing techniques or different models, data scientists must carefully create many-step manipulations in visually distant cells. In our formative interviews, we found data scientists had adopted behaviors ranging from fastidiously keeping track of variable name variations to managing many nearly identical copies of a notebook across different files. These interviews yielded design principles for a tool that could support this process. First, the tool should allow data scientists to easily express alternatives and decision points. Second, the tool should allow data scientists to navigate execution history, easily returning to previous states. Finally, the tool should make it easy to visualize and compare alternatives, such as the performance between different models. This paper introduces a new tool to help data scientists more directly express and navigate decision points in a single notebook. The tool supports forking, or creating a new interpreter session, and backtracking, or navigating through previous execution states. Forking provides data scientists access to multiple interpreter sessions. At any point, a data scientist can create a fork, splitting the cells below into multiple paths. This creates a new kernel for each path, each of which run independently from each other. For example, in this case, both are writing a number every second, but the variable updates do not interfere with each other. Our system provides independent kernel run counters as well. Each run count is prefixed by a kernel ID, followed by the cell run counter. When creating a fork, two decisions must be made. The first is where to visually create the fork in the notebook. The second choice is what interpreter state to use. That is, what should the values be for each variable in the new paths. While the previous interaction focuses on where to create the fork, backtracking focuses on what interpreter state to use. Consider a data scientist exploring several models for a dataset. In this case, they have just gotten a random forest model to work. Now that it's working properly, they'd like to explore some other models. When they select Backtrack, a modal appears with the last cell that was executed and the current variable state. For example, the most recent executed cell computed the test and training scores. Those newly created variables are present in the list, along with the current values of other variables that had been computed previously. The left and right arrows allow the user to navigate through the execution history, regardless of how the cells appear visually in the notebook. At each step, the modal updates. In this case, note that the score variables are no longer present in the list, as if the cell that had created them had been undone. For variables like data frames, which can be quite large, summary data is shown, specifically shape and columns. Once they find the correct state, in this case before we created the model, they can press the backtrack button. This creates a fork with a new path at the selected state, visually placing it based on the topmost visible cell whose code was undone. They can then copy or modify code as appropriate to explore other models. In our qualitative evaluation, we had 11 data scientists use this tool in a model prediction task. They used forking and backtracking to support a range of behavior, including comparing decisions and parallelizing the workflows while long-running cells executed. Participants also used forking and backtracking to support debugging, using paths to isolate messy exploratory code, and using backtracking to undo regrettable code such as unintentionally corrupting a data frame. Users found utility and desire to incorporate forking and backtracking within their data analysis workflows. This work suggests that further exploration will be fruitful, particularly around more effective interfaces to manage branches and compare various paths.